All right. We're finally going to solve higher order differential equations. So today we're talking about homogeneous, linear differential equations with constant coefficients. So I want to start by looking at a first order linear homogeneous differential equation with constant coefficients. So a y prime plus by equals 0. And I'm going to write this out. I'm going to write it in, just write it in a different form. Y prime equals negative b over a times y. And we could write this negative b over a is just a constant. These coefficients are constant. So we could say that's just k times y. Well, this is a nice separable differential equation. Y prime is dy dx. So we could write dy over y equals k dx. And we've solved this equation, equation very similar to it, a number of times. We know we get exponential solutions because this is a natural log, and so we end up with an exponential. And I'm going to write that as y equals e to the mx. And in this case, m would be negative b over a. Now, if we look at this equation, and we've kind of alluded to this in some of the homeworks, we've asked questions like this in the past, the exponential function is the only function that we know where multiples of the function and its derivative could add to 0. So what if we just assumed, instead of doing this work, what do we just assume that the solution to this, based on the fact that an exponential function, if we add exponential functions together, we can, the exponential functions and their derivatives, we can get 0. What if we just assume the solution is an exponential function? So start by assuming y equals e to the mx is a solution. And we say, what does this imply? Well, if you think back, we've done homework questions like this as well. So I'm going to take the derivative, multiply it by a, add it to b times this function. We need that to equal 0. So we get a m e to the mx plus b e to the mx equals 0. And I can factor out that e to the mx, and we get a m plus b, and that has to equal 0. Well, if m is not 0, e to the mx is never 0. So we have to have that am plus b equals 0, and that tells us that m equals negative b over a, which is what we had here. So just based on that observation that, well, the exponential function is a function where we can add multiples of the function and its derivatives and get 0, assume that that's our solution, and what does that imply? Well, we get the same answer. So we're going to do that same thing with higher order differential equations. So now we want to look at ay double prime. So we'll start with the second order differential equation plus by prime plus cy equals 0. So linear second order homogeneous differential equation with constant coefficients. And we know this has a general solution because our coefficients satisfy our conditions for having a general solution. So we're going to assume that y equals e to the mx is a solution. And we're going to see what that implies about m. Well, we take our first derivative and our second derivative, and we substitute. And we get that am squared e to the mx, that's our second derivative, plus bm e to the mx plus c e to the mx equals 0. And again, we've done this kind of homework problem before. It was kind of getting us mentally prepared for what we do here. Again, we factor out the e to the mx, which is never 0, and that implies that am squared plus bm plus c has to equal 0. We call this the auxiliary equation for the differential equation. So we start with a second order linear homogeneous differential equation with constant coefficients, and we get this auxiliary equation. So m squared corresponds to the second derivative, m corresponds to the first derivative, and our constant corresponds to just the function, the 0th derivative. And we can, since this is a quadratic equation, we can either factor or use a quadratic formula to solve for m. So in general, I'm just going to write it as quadratic formula. In general, m1 is going to be negative b plus the square root of b squared minus 4ac over 2a. And m2 is going to be negative b minus the square root b squared minus 4ac all over 2a. So we get our two constants, we get our our family of, our two parameter families of solutions. And our solutions then our solution is y equals c1 e to the m1x plus c2 e to the m2x. But we have a wrinkle here. We have three possibilities. I'm going to put a little asterisk here, because we have a couple of things that can happen that we need to be careful of. Three possibilities. M1 and M2 are real and distinct. So that occurs when b squared minus 4ac is greater than 0. In the case where m1 and m2 are real and distinct, then our general solution is y equals c1 e to the m1x plus c2 e to the m2x. Our second case, this is where we start needing to be a little careful. M1 and M2 can be the same. M1, M2 are real and equal. And this is the case when b squared minus 4ac equals 0. And in that case, M1 equals M2 equals negative b over 2a. So we have repeated roots. Well, in that case, the solution is y equals c1 e to the m1x plus c2 e, I'm going to say m2, but m1 and m2 are the same, c2x e to the m2x. Does anyone want to take a wild guess how we get this x e to the m2x, given that we have this solution? We have a second order differential equation. We have one known solution. How would we come up with a second solution? Yeah, we do from the reduction of order. So our second solution comes from the reduction of order. So this is what I was talking about yesterday. When we see a certain kind of solution, we know that reduction of order gives us this. So when we get an e to the mx solution, the reduction of order gives us x e to the mx. So then we have our two-parameter family of solutions. Here's where it gets really interesting. And this part of why I wore the algebra quadratic formula shirt, because we end up using the quadratic formula. Our third possibility is M1 and M2 are complex conjugates. So M1 equals alpha plus I beta, and M2 equals alpha minus I beta. We get conjugate pairs. And then our general solution is y equals C1 e to the alpha plus I beta x plus C2 e to the alpha minus I beta x, which we rewrite. I'm just going to rewrite it in slightly different form. I'm going to use properties of exponents here. C1 e to the alpha x times e to the I beta x plus C2 e to the alpha x e to the minus I beta x. Now we need to make sense of this. So what we do here, and I talked about it very briefly in pre-calc. I've alluded to it a number of times over the course of this year. We rely on Euler's formula, which to me is like a miracle. Euler's formula tells us e to the I theta is cosine theta plus I sine theta. So we have this relationship between the exponential function, complex numbers, and trig functions. This is, to me, this is the big review today. When you get complex solutions to our differential equation. That leads to trigonometric solutions. So we write this as y equals c1 e to the alpha x times cosine beta x plus I e to the alpha x sine beta x, and we get one for here. We get y equals c2 e to the alpha x cosine beta x minus I e to the alpha x sine beta x. And we don't want that, that imaginary unit in there. We don't want that I in there. So what we're going to do is we're going to rely on the superposition principle. If we add these two together, I can leave the constant off, we'll deal with the constant at the end. We get 2 e to the alpha x cosine beta x. And we divide, so we add the solutions. We know the sum of solutions is also a solution, and then we divide by 2. So we add the solution, we get 2 of these, divide by 2. So one solution, yes?
Why do you divide by 2 rather than just moving it as part of, like, say it's part of the constant?
You could say it's part of the constant, but yeah. But I'm just the way I thought about it. We add and divide by 2, and we get add, divide by 2, and we get y1 equals c1 e to the alpha x cosine beta x. And then we're going to subtract. Well, if we subtract, we get 2I e to the alpha x sine beta x, and then we divide by 2I. Because sums and multiples of solutions are still solutions. And we get y2 equals c2 e to the alpha x sine beta x. So when we get complex roots to our auxiliary equation, that leads us to these trigonometric solutions. Yes?
Wait, why don't we just, like, add them together so that those things cancel?
That's what we did for the first one. We added them, and we got, then divided by 2, and got this one. But we also have the possibility of this sine solution. That's why we subtract them and divide by 2I to get the sine. Because we know we need a 2-parameter family of solutions for a second order differential equation. So our general solution then is for the case where our roots are complex conjugates. For this case, our general solution is y equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. So a couple of big things here. Solving these higher order differential equations with constant coefficients comes down to factoring polynomials. And we have this relationship between our exponential function, our complex, our imaginary unit, and trig functions that give us exponential functions and trig functions as solutions to these differential equations. And we know that we can combine exponential functions and get hyperbolic functions. So we get exponential functions, trig functions, and hyperbolic functions. as solutions to these things. To me, that's like you kind of opening up the, peeling behind the, opening up the curtain and peeking behind and seeing kind of a little glimpse of how the universe operates. All right, questions? Mm-hmm.
When you were saying like subtract, what was being subtracted?
Subtract the second equation from the first.
Okay.
So if I subtract, the cosine terms go away, and I get e to the alpha x sine beta x minus negative
Yeah.
I e to the x. So I get two of those.
And why don't we care about the left side? Just like, we might just count zero out or like what?
Yeah. So the addition gets us the cosine term, and the subtraction gets us the sine term.
Yeah,
So then,
with the addition, you're gonna get like 2y, right? Is that the idea?
or
is those
well,
completely
just
separate?
we're adding those two solutions. If I called this y sub a and y sub b, I get y sub a plus y sub b
Okay.
is that sum. But we know the sum of a solution is also a solution,
Okay.
so I just call that another solution.
So yeah, it's just that they're distinct solutions. Y a or y1, y2, whatever.
Right. Right. Yeah. So just doing the operations, we just call them two different solutions, but they're all a portion of the general solution. All right. So I want to look at some examples. And we saw, I'll just go back, we saw that solving the solutions to homogeneous, or some non-homogeneous differential equations involves solving the homogeneous differential equation first. So what we are doing today is kind of the foundation for solving non-homogeneous differential equations as well. Did I tell you that when my son was young, he had an imaginary friend? I asked him how he knew that his friend was imaginary, and he said, because when I multiply him by his conjugate, he turns real. And we want to solve this. Linear homogeneous second order differential equation with constant coefficients. Our auxiliary equation is m squared minus 3m plus 2 equals 0. This is a nice auxiliary equation because we can factor it. So this tells us m equals 2 or m equals 1. And our solution is y equals c1 e to the 2x plus c2 e to the x.
They're all gonna be that easy, right?
And notice as x approaches infinity, y is going to approach infinity here. So this differential equation probably would not model very many physical situations. There are not a lot of physical situations that grow exponentially. What's that?
Easy to solve.
Easy to solve. We could change some signs around and have these both be negative, and then we'd have decaying exponentials, which is a little more likely. Y double prime minus 10y prime plus 25y equals 0. Well, this, our auxiliary equation, is m squared minus 10m plus 25 equals 0. And that's m minus 5 squared. So m equals 5 and 5, repeated root of 5. So we would say y equals c1 e to the 5x plus c2 x e to the 5x. Pretty easy, right?
Yep.
2y double prime plus 2y prime plus y equals 0. Our auxiliary equation is 2m squared plus 2m plus 1 equals 0. This one does not factor, unfortunately. So quadratic formula. If we do the quadratic formula, we end up with m equals negative 2 plus or minus 2i over 4, which is negative 1/2 plus or minus 1/2 I. So our general solution would be C1 e to the negative x over 2 cosine x over 2 plus C2 e to the minus x over 2 sine x over 2. And this one, as x approaches infinity, y approaches 0. So this one may be some kind of model for some kind of physical situation. We get a decaying trig function type of solution. So like some kind of thing oscillating with friction, eventually going to 0. Now for higher order equations, third degree, fourth degree, fifth degree, the process is exactly the same. We write the auxiliary equation and we find the solutions to the auxiliary equation. The difficulty then comes in solving the polynomial equation. So we have a fifth order polynomial that we have to find the zeros of. So for that, we are relying on our tools that we learned way back in pre-calc. Okay.
Yeah, it's like digits over, we can't, you know.
What's that?
If it's like a fifth order, we can't put that in the computer and use
Well, it depends. I mean, I wouldn't give you a fifth order, probably not give you a fifth order polynomial on a test, but maybe a fourth order polynomial. So, rational root theorem, the P's and Q's, synthetic division, finding a zero remainder, Descartes' rule of signs to help us out with the positive real zeros and negative real zeros. All of those tools that we learned in pre-calc come into play when we're solving these polynomial equations. So that's where the difficulty with the challenge with first order linear, not first order, higher order linear differential equations with constant coefficients comes in finding those zeros. And if you, technology is very good at finding zeros. I would say you should probably also be pretty good at it. Because the more you use technology, the less good you get at it. Yes?
So like besides like quadratic formula, like factoring and like the groups one, like are we gonna need to know like synthetic division?
Yeah.
We're gonna have to I don't remember any of the problem.
Yeah, you don't really do much factoring. And I mentioned Descartes' rule of signs. Right? Yeah, the plus, where you look at the sign changes. So Descartes was the mathematician, French mathematician, we named the Cartesian plane after. He developed or kind of popularized Cartesian coordinates, coordinate geometry. Once there was a horse that they were teaching math, and the horse could learn all kinds of math. Could learn algebra, learn some geometry with shapes, could even learn a bit of calculus, but would not learn anything to do with coordinates. Do you know why? They were putting Descartes before the horse.
That's actually pretty good.
So, and for higher order differential equations for repeated roots, if there are multiple repeated roots, we have to include higher powers of x in front of our exponential term. So back here where we had an x, e to the x. If we had 3 repeated roots, we'd have a c1 e to the something x plus c2x e to the whatever x plus c3x squared e to the whatever x. And those all come from using the reduction of order. And for some equations, you kind of have to use technology. So if we had something like 4.35 y triple prime minus 3.85 y double prime plus 2.32 y prime plus 1.073y equals 0. Finding the zeros of that thing, that's challenging. So you're going to get an approximation here. I put a Wolfram Alpha widget that's just a general differential equation solver in our little folder that you can plug that into and solve. Or you could write the auxiliary equation and use some technology to help you find the zeros of the auxiliary equation. Yes?
If you have like more than 2 complex, like you have 2 sets of complex conjugates, would that happen? What would the general solution be?
Yeah, that could happen, and then you just have c1 e to the alpha 1 x cosine beta 1 x plus c2 alpha 1 x sine beta 1 x plus c3 e to the alpha 2 x cosine beta 2 x based on the roots of that polynomial.
Okay.
So you just have multiple exponential and trig functions. If you have a pure imaginary 0, then you just get pure sines and cosines. You don't get that e to the alpha whatever multiple. You just have pure trig functions. All right, let's look at a higher order example. Y to 4 prime minus 6y triple prime, no, double prime, this is a 3 prime, plus 12y prime minus 8y equals 0. Auxiliary equation is m to the 3rd minus 6m squared plus 12m minus 8 equals 0. Not a factor by grouping. So for this one, what I did, that's my p, that's my q. Plus or minus p's over plus or minus q's is plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Descartes' rule of signs. This one has 1, 2, 3 sign changes. So that's 3 or 1 positive. For negative m, if I plug in negative m, I get negative m to the 3rd minus 6m squared minus 12m minus 8. So there are no sign changes here. So there are 0 negative real zeros. So I'm only going to focus on positives. I plugged in when m equals 1. It's easy to plug in. That's just 1 minus 6 plus 12 minus 8, which is not 0. When m is negative 1, I'm just changing the signs on the odd powers. So it's going to be negative 1 minus 6 minus 12 minus 8, which is also not 0. So then I would start with m equals 2. So I'm going to do my synthetic division. 1, negative 6, 12, negative 8. We get a 0 remainder. So that means m equals 2 is 1, 0. This is m squared minus 4m plus 4, which is m minus 2 times m minus 2. So I have a triple repeated root. So our factors is m minus 2 to the third. So my solution, y equals c1 e to the 2x plus c2x e to the 2x plus c3x squared e to the 2x. Shall we look at one more? Let's factor one more. What's that? We're kind of doing it right now. That was too many. Auxiliary equation is m to the third minus m squared minus 4 equals 0. My possible roots are plus or minus 1, plus or minus 2, and plus or minus 4. There is one sign change here, so that tells us there is one positive. So I'm going to go after that positive one to do synthetic division with. So if m equals 1, that's easy to plug in. I get 1 minus 4, which is not 0. When m is 2, because this is not many terms, I'm going to plug in 2. I get 8 minus 4 minus 4, which equals 0. So now I'll do my synthetic division. 1m to the third, negative 1m squared, 0m minus 4. Don't forget you have to put a placeholder in there. So now we have m squared plus m plus 2 equals 0. That one does not factor. So we use the quadratic formula, and we get m equals, when I use the quadratic formula here, I get negative 1/2 plus or minus I square root 7 over 2. So y is going to be c1 e to the minus, oh, I forgot one, let's see, this is m equals 2. E to the 2x plus c2 e to the negative x over 2 cosine square root of 7x over 2 plus c3 e to the minus x over 2 sine square root of 7x over 2 for the solution to that. It gets more interesting if you have a 4th degree polynomial or higher.
That's like, you sound too disappointed.
What's that?
You sound disappointed that you don't get to do it.
I mean, factoring polynomials, you do it enough, and it's like, oh, this is easy.
Look at that solution.
Yeah, look at that.
You know you're doing like math. Math.
All right, questions? So on Monday we're just basically we're having a work day to do more of these, because the process of doing these, coming up with solutions, making sure you include the correct terms in your solutions, it's kind of the foundation for a lot of what we're doing, what you do moving forward. So I want to make sure we practice doing that.
Wait,
Uh,
can you give us more on Monday, or is it just going to be the work on this one?
There's more on Monday. And then on Tuesday we have our quiz.
On this.
Shucks.
And the quiz will have a little bit of solving on it. And some hyperbolic function stuff from section 5.8.
Well, I just do to get that right.
Do I have to like the derivatives and the?
Yeah.
Okay. I got like this note card.
And then you check how many flips there are, and what's the significance of one flip?
That means with one positive real zero.
Yeah.
But if there's two flips, there's two positives.
2 or 0.
So you go like down by 2. So if
Oh,
you-
and then
if there's
three
three
is
sign flips,
three
you
or
3
one.
and 1.
Oh,
If you
okay.
have 5, it'd be 5, 3 and 1. Or 1.
Five. If there's 5 sign flips, I'm not doing the problem.
Wait, is
Because
this
you
sign
give us
change?
these like long, they have like 7 turns in it, and it just you count the sign changes. Once you know that, it's acceptable.
Is this why we factored so much, or not factored? Just
Yes, this is part of it, because it's one of those things that when you're doing it, it doesn't seem that important, but then it comes back and it just never, factoring polynomials is something that never goes away.